large language models from transformers to GPT. Our session speaker is Dr. Ahmad Rimaz Faizabadi. Sir has obtained his graduation in computer science and engineering from Vishweshwara Technological University, Belagavi, MMES, Belgaum. He has obtained his MTech in computer science and engineering from RV College of Engineering, Bangalore. And he has also completed his PhD in artificial intelligence and machine learning from IIUM, Malaysia. Sir is currently serving as an assistant manager in Deloitte R&D, Malaysia. He is expert in AI and computer vision software development, IMAP, AVC, high speed weight and motion. He has served as a system architect, has done automation with detailed performance analysis of WIM. He's developing various data centric AI and agnostic AI methods to improve AI models. So it's so privileged to have you as a session speaker with us today, sir. Very hearty welcome to you. You can take over the session, sir.
Thank you, ma'am. Can you see my slides, madam?
Yes, sir.
Yes, sir.
Good evening to everyone. This is the second session of the today's FDP program, the architecture behind large language models from transformer to GPT. I myself, Dr. Ahmad Rimaz Faizabadi from Deloitte R&D, Malaysia. So I'll be your presenter or the resource person for this session 2. So we will be having the brief agenda. Basically, we are going to have introduction on generative AI, LLM. We will check the background of NLP. We will see how the NLP used to be done before 2017, like RNN, LSTM, word to vector. And our main focus of this talk will be around transformer and self-attention. Basically, the main goal will be to understand the paper attention all you need. Okay, so based on that, the BERT and GPT architecture will be understood, and then we will have certain uh, uh, background discussions like what is pre-training, fine-tuning, prompt engineering, what are the limitations and challenges, and then we can end up with a question and answer session. So our main focus will be on transformer and self-attention. So before starting the session, we need to know why I'm joining this session, what I will be able to do after attending this session. So there are many words, many terminologies that we are going to go through in this and try to understand them in detail in context of large language models. So basically, you need to understand in deep learning is a very broad area where we have certain deep neural network architectures. Why we call them deep? Because their hidden layers are usually more than 3, means they are deep architectures. So the kind of architectures that we use in deep learning are varied depending upon the task. Okay, but based on the uh, type of work, we can say they are of 2 types, discriminators and generators. Okay, so like normal CNN, which performs an computer vision task like identifying cat or a dog, is basically a discriminator network, which need to discriminate between cat and a dog. Cat and a dog. Okay. But here in this talk, we will not be talking about this kind of networks. We will be talking about special networks which basically do the generation. For example, if I have the generator which generates an image, identifying fake or not fake will be a discriminator. When the study will happen between these two, there will be a different field of deep learning called generative adversarial networks. Lot of focus right now is going on generative AI, and in generative AI, which is not of my current focus, is about the diffusion models and latent diffusion. Why they are used? Because the GAN, or what we say generative adversarial networks, loss function is very complex, very difficult to train, lot of issues. So we go for something called latent diffusion or diffusion. Basically, diffusion brings up, reduces that complexity of the loss function, but however, it will bring the learning stability. Okay, whereas discriminator part, okay, here will be through the diffusion or latent diffusion. So that is a totally uh, different field that we are not going to touch upon. So in this talk, what we are going to familiarize, what is text embeddings, position encodings, residual, what is query, key, value, what is attention, what is self-attention, what is masked attention, what is encoder and decoder. Basically, encoder and decoder are two types of networks. Encoder is basically which generates an embedding or encode the input, and decoder is something which actually generates something or decodes the input embedding or reproduce the same thing. Okay, so here we are going to end up with only encoder and decoder models, that is BERT and GPT. So basically at the end of the talk, you will be familiarized in detail what is the attention, what is mass attention, what is multi-attention head, etc. Okay, and what is uh, encoder and decoder doing in large language model or NLP tasks. So how do we define the generative AI? Generative AI is a type of artificial intelligence technology that can produce various type of content. Okay, the content can be text, images, audio, it can be any synthetic data, etc. Okay. So how the generative AI works? Basically, it's a subset of machine learning where AI models learn statistical patterns from vast amount of human generated data. Okay, basically in a nutshell, for the language models where we have text to text generations, etc., we have trained up trillions of tokens over a long period on very high computing resources. Means basically the things that we call foundation models are very resource intensive and data intensive. The amount of data that is required is massive, and amount of computation is also massive. Okay, it takes over sometime over the weeks to train one foundational model. Okay, what is different between foundational model and large language model? Basically, foundational model tries to capture the entire details of this real world or the knowledge base. Okay, for which the model is being trained. However, they can be using multimodality. Means the input can be of different types. It can be a sequence inputs like text. It can be a time series. It can be a image. It can be audio. It can be different sensors, IoT, whatever it can be. Okay, so the main difference between LLM and foundational model is most of the foundation models are having LLM capabilities, but all LLMs doesn't have the foundational model capabilities. Okay, largely if you see every big corporate have developed their own LLMs. Okay, and right now most of the LLMs like Grok, Llama, uh, Cloud A are version 4, whereas ChatGPT has already released the version 5. So basically what this LLM do, they learn to comprehend and generate human-like language patterns. Okay. So for what purpose they try to comprehend this text or these inputs and generate like language patterns, human-like language patterns, basically to do the various LLM tasks such as summarizing text, translating text, converting text to a code, generating essay based on the topic, making a question answering system, and so on. Okay. So basically LLM excel in next word prediction, which forms the foundation for various capabilities. Okay. Any doubt here? I'm audible, right? And my presentation is visible, right?
Yes, sir.
Okay, thank you.
Yes, sir. Go ahead, sir.
Fine. So this is a uh, map of evolution of natural language processing. It started in 1980s with something called recurrent neural networks. However, these things will not pick up because of there was no massive parallel programming capabilities were available like the GPU has provided in recent years. Okay, in 80s, such capabilities were not there computationally. Okay, probably what is the computer? What was the supercomputer of 2000, which was listed in top 500 by CDAC, may not be even listed anywhere now. Okay, or your mobile is more powerful than that supercomputer. For example, if you consider a supercomputer series by CDAC, we have something called uh, Param series, where we have Param Padma, Param Yuva, etc. So initially, when these Param machines were commissioned, they were commissioned for the computational power of 1 teraflop. Okay, by assembling the 1024 computing nodes, which are capable of performing 1 gigaflop operations, we built the first supercomputer named Padma. Okay, then it was extended when I was working on it in 2016 6 during my master's in Bangalore. Okay, basically it was extended to a capability of 4 teraflops. Okay, now we have the exascale computing. Okay, the single uh, GPU based mini computer, which is DGX Spark, released recently by the NVIDIA DGX Spark, which uses Blackwell technology of GPUs. Okay, can perform 1 petaflop operations of FP4 floating point precision. Okay, so can you imagine like 1,000 supercomputers within a small box like your tiffin box, and it does not weigh even more than 1 or 2 kg. Okay, that is an advancement basically which followed, which has push this development. It's not alone the what you say architectures. Architectures were there. Even CNN was there for long. Okay, but it could not be harnessed. Its potential could not be harnessed until we got the CUDA platform for parallel computing and the GPU resources which can provide the computation at cheaper cost. One of the important thing that you need to consider when you are considering computing. For example, if you are talking about ethics related to AI or LLM, you may be talking about data centers. And one of the important thing with data center is power consumption. Okay, they take a lot of energy to run these GPUs. Okay, previously it was too much. Okay, like to run a Param Yuva, which was in Pune, the amount of it was around 124 teraflop operations that time, not even petaflop computation. Okay, it used to consume more more energy, means electricity, than what the Pune entire city could consume in a day or a week. Okay, so what entire week we consume in a city might have been consumed. Like you require a HPC, I mean supercomputer, you require a nuclear or thermal power plant also next to it, like 20 megawatts, something like that. So because of this low power VLSI and parallel programming architectures, we were able to compute the large neural networks. And we were able to fit large neural networks in the memory. Earlier, it was not possible. So it's not just a lots of data, it's a growing computing power and open source. One of the important thing in the development is open source technologies. Lot of thing that is being even developed by Meta, okay, uh, Google, everything is like open source. Okay, and the community of the open source developers are contributing to it. Now, if you see, the PyTorch is in true sense is an not proprietary for any company. It's an foundation like a Linux or the other open source technologies. Because of this, fast iteration on ideas were possible. So already you know that RNN, we started doing the sequential processing. Okay, then we improved it using LSTM. I'll go in detail about these three things as a pre-2017 era. But what is very important and significant change happened in in the field of NLP is in 2017, the transformers were developed. Okay, the main paper is attention all you need. Okay, so this is a paper is a focus of this talk. I'm going to explain this paper in I cannot say very comprehensively, but in a required detail so that you will build very solid foundation for the next coming sessions and even can take up some LLM projects which are feasible to you. Okay, then immediately when in 2017 this transformer were developed by basically a team of Google scientists. Excuse me. Any issue, madam? I'm not able to see the teams. Okay, I'm looking at my PPT. That's why if anything is there, please interrupt me. Okay.
No, sir, you're fine, sir.
Okay, all right. So what is happened in 2013 is it gave the rightful idea how to use the text in neural networks, because you know the neural networks could not consume the words. They require numbers. They crunch the numbers. Okay, and usually in form of tensors. Okay, the larger the tensors, we because of the compute power, we are able to crunch them down to anything. Okay, they can be any number of. Currently, we are even going to trillions of parameters. Okay, but if you consider the trillion of parameters, is just like a brain of the mouse. We didn't reach the brain of the human yet. Okay, there is a lot of gap. Okay, we were able to successfully develop the neural networks, which are just as good as in number of synapses. Okay, means network connections, neural network connections. Okay, like honeybee to mouse, we are in that range. Okay, you know the mouse uh, has like around some 30 trillion parameters or synapses that it can work with. So we are in that range. Okay, but comfortably we are dealing right now up to 200 uh, billion parameters in DGX Spark, uh, DGX Spark. Okay, so this is the tiniest supercomputer that if you are interested, you can look into it. And this is what most of universities or colleges can afford, according to me. Okay, other GPUs which are very high end, very difficult to afford. Okay, they require high investment, very high cost for running and maintenance. Okay, something which may not be even feasible for uh, some constrained researchers. Like upfront 2 crore investment cannot be possible by a research center. Okay, but 3 to 4 lakh DGX Spark can start uh, building the LLMs or fine tuning the LLMs that you really want to dream of. Okay, and can move to the agentic AI. I'm not talking about AI agents. I'm talking something very different, agentic AI. Okay, so now because of this 2017 transformer, which was basically a Google paper. Okay, let me switch back to the browser mode. It was published in Newer IPS, one of the premier places for. So this was developed by Google Brain, a scientist. Okay, all of them were working in Google Brain and Google Research, and they have developed an open source transformer. So basically, my talk is about explaining this network or the architecture. Okay, transformer. Then immediately, based on this technology, the BERT was released and then GPT-1 was released, which are basically two very distinct approaches and very interesting. We will try to look into that also in detail, and then we will glance other models. Okay. Right now, the things like DeepSeek R1 or V3, R1 V3, Llama 4 have really crossed the things, and GPT-5 is basically making very remarkable contributions. So basically, if you see in 80s and 90s, we started developing sequential processing neural networks. In 2013 around, we were really able to conquer a basic thing called word to vector or a foundational embedding method. Okay, so if you have seen in the first session, the speaker was showing you lot of embedding models. What basically these embedding models are? Basically, these are basically a means to convert uniquely uh, and discriminatively the different text tokens. Okay. If there are more discriminate and more powerful embeddings, what is powerful embedding? I will try to explain through the code. Okay, I will be taking through you how to extract the embedding once I reach the appropriate slide, right? So basically, this is the timeline of the NLP models. Right now, what is happening is the researchers or academicians are overwhelmed. The amount of information or the papers or the research because of fast iteration on ideas with help of generative AI, with help of low-level code support means basically what we could do earlier in years, is possible in few hours. That is the amount of pace the research is going right now. So it may be very difficult to have a grasp on the entire spectrum. But if you have the goal, what you want to develop, and you know the follow the path over few weeks, over few months or year, when you work on uh, systematically, definitely you can become an expert of the field. Okay, earlier, or if you go by rule, minimum 10,000 hours you need to spend on anything to become a master of it. Okay, so that's how the most of the universities keep the PhD requirement as 3 years. Okay, but to understand the 80% of it, you just require few hours. Okay, that is what this FDP is trying to do, and try to ignite the minds in a right direction. Okay. So basically, NLP task can be classified as classification or multi-classification or generation. Basically, sentiment, like it's positive or negative sentiment, is just a classification task, even though it's a input is text, but the output is like it's a positive emotion or negative emotion. Okay, whereas multi-classification is basically it will provide some text and some limiters. Okay, and the generation is the input is the text and the output is also text, like summarization, machine translation. So basically you give the English language sentence and it is being translated to in another language. So NLP task, when we are having classification and multi-classification, the metrics are very similar, like accuracy, recall, precision, F1 score. But when we are going for generation or generative AI, like input text, output text, we cannot apply these metrics to evaluate or to determine the goodness of our model. Okay, so for that we have certain evaluation criterias that also I'll try to discuss with help of example. Okay, so what is the first thing we need to do? The foundation of any NLP is tokenization. So basically, what is a tokenization? Take the text T, divide it into understandable chunks. Divide it into a understandable chunks. Are you clear with me? Okay, you have the text like teddy bear. Okay, so you consider this as one word, that is a tokenization. You consider teddy as separate and bear as separate. For example, run, running, runs. Okay, all have certain common parameters. So you want to break it run and yes separate, run and running ing separate, run and other part separate. How you want to divide it? Okay, for this division of the text, okay, we call tokens. Okay, most of the models that you want to use in a paid format, they work on number of tokens that you have used or number of tokens you have generated. Okay, so token is a currency. Token is an currency in terms of NLP and large language models or the language models. I hope I'm clear with it. So tokenization is process of breaking down the text into smaller, meaningful units called tokens. Okay, these tokens serve as basic building blocks that language model use to understand, process, and generate text. You can divide them into words, subwords, characters, depending upon how well meaningful you want to make. So if you take teddy bear as one token, you are basically using only one token, but teddy as separate, bear as separate, then teddy bear is a two different tokens. But if you want to make D, okay, as a separate adjective. Okay, and then you break it with T hash edy and beer, then you got more tokens. The more tokens means more computational cost, more training time, more cost when you run the model. Okay, so basically when you are subscribing to the paid models like Cloud A or ChatGPT, O5, etc., basically every token matters. So how you divide the token is suitable for the task. Okay, so tokenization will matter the efficiency, understanding of the language, vocabulary, and flexibility. Okay. So here is an example, hello world. So I generated them into few tokens, hello, comma, world, and exclamation mark. Okay, like tokenization, token separateization is separate. Okay, like teddy bear AI models, not as a one word, AI separate, model separate is another example. So what are the use case? In every LLM like GPT, Cloud A, whatever AI models you use, tokenization is the first process. Okay. It is used in machine translation, search engine, sentiment analysis, text classification, everywhere. Okay. Now let's move to recurrent neural network. Just a second. Excuse me, please. So basically, if you see the recurrent neural network, basically it's a neural network, okay, where the HT is computed as a function of HT minus 1 and XT. Are you able to follow me what I'm saying? It's a function of HT minus 1, comma, xt. Okay, because the previous input is required, previous output is required. Okay, previous output is required to generate the current output. You cannot do them parallelly. This is one of the main constraint of the recurrent neural network. They are able to make sentence in a natural language. Okay, like sequence modeling is possible. Okay, we can generate the concept vectors. The last output that is being generated by the end of the encoder is called concept vector. Okay, means we can do the processing. So H, so what is xt minus 1, xt plus 1? These are the tokens. Okay, these are the tokens of your sentence. Okay, now if you are to compute the function of xt, okay, means you have to compute st, you require st minus 1 and xt. Okay, without computing st minus 1, you cannot generate ht. So this is very sequential. So this is the main bottleneck. So what happens because of this, the recurrent neural networks cannot remember for long. They exposed to vanishing gradients, exploding, and more importantly, they are, even though we have parallel uh, hardware, we cannot use it effectively. Okay, so RNN can be used for classification like sentiment generation. It can be used for multi-classification like tag generation, or it can be used for translation. Okay, for all the type of task, RNN networks can be used. Okay, so basically, if you see normal neuron, okay, we have WX plus B. Okay, here we basically each neuron here requires a previous input, and that becomes a bottleneck. but introduces a concept of memory because it is taking the previous sequential data output like ht minus 1. So to improvise this, the new model was proposed called long short-term memory network. Okay, uses more structured approach in a cell hidden state. Basically, if you see, there are more component-wise copy and concatenate operations in the layer, sigma or tau. Thus, gradient values are not attenuated, means vanishing gradient problem will not happen. But still, it's a sequential processing, an improvised one. But however, it's a sequential processing, means cannot be parallelized. Then in 2013, the landmark thing came called word to vector, where we could convert the word to a embedding. Embedding is nothing but a unique vector for that text. Okay. So to develop a word embedding, we enable the model to understand meaning based on the context and then generate one unique embedding. So to learn embedding, we use the two different methods called continuous bag of words or skip grams. So what is a continuous bag of words? The first example that you see, teddy bear, is given to me the word. I need to guess all other words. So context words are combined, often averaged to predict the word that should fit in the gap. Okay, sorry, I talk it reverse. So I have been given a cute blank is reading. Okay, I need to guess a word for a cute is reading. Okay, whereas in the skip gram, to predict the constant words given a single target word. So only teddy bear is given. I need to predict what comes before it and what comes after it. I think I was saying it correct. The bottom example is for continuous bag of words and upper example is for skip grams. Sorry for confusion. So let me repeat what is continuous bag of words. Word is given like teddy bear and I need to predict the context words for this target word. Like if teddy bear is given, I need to generate the bag of words called a cute is reading. Okay, all this is essentially reverse the task. Okay, so basically now if you want to summarize what we have discussed in pre transformer era till 2017. Okay, we got the embeddings. Okay, simple but powerful, but words order does not count. Embeddings that we have generated are not context aware. Okay, whereas RNNs like RNN and LSTM, word order is very important. Vanishing gradient will happen and there is a slow computation because of the computation cannot happen until the previous node is computed. For ht, I need to compute f of ht minus 1 comma xt. Okay. So the way to move forward is to start using attention. The attention was used in 2014 and 15, mostly for a neural machine translation. This is a paper, basically neural machine translation is a task. But the paper name is Neural Machine Translation by Jointly Learning to Align and Translate. All right. So the traditional encoder decoder RNN model had a major flaw. The entire meaning of the source sentence had to be compressed into a single fixed size concept vector. Okay, means the sequence to sequence method was unable to remember the long input. Okay, it was hallucinating. Okay, kind of hallucination. Okay, not able to know what to do. So basically what is an attention is, I'm going to repeat attention so many times with a different perspective, okay, until we reach the transformer, right? So if you have any confusion, you can ask me to pause and rediscuss it. So encoder, instead of compressing the entire sentence into single concept vector, it produces sequence of hidden states. So earlier the encoder used to produce, for example, there are five tokens. So H1 will be calculated, H2, H3, H4, H5. After H5, the output of H5 from the encoder used to be called as concept vector, or only single vector used to be fed to the decoder. Now we will pass all H1, H2, H3, H4 along with the concept vector. So it produces a sequence of hidden state. Whereas decoder is about to generate the ith target word, it will not rely on a single word. It will consider the what is previous hidden states or values. Okay, means if H5 is being generated, H1, H2, H3, H4, all will be available to consider what relation or how strong they are. Okay, so for example, when I say teddy bear, okay, this is one word or maybe say two tokens. Okay, and soft is another token. Okay, so how do you correlate these two words? They are very close or far? Teddy bear and soft. They are close or far? They have connection or they don't have the connection?
They are close.
So if you have the teddy bear, okay, like the toy teddy bear, you usually use it to comfort because of its softness, smoothie, and what you say, feather-like touch. Okay, so these two words need to be very close in the distance when we generate this uh, what you say, tokens or embeddings. Okay, so what is the difference between token and embedding? I will explain you with an example program. Okay. So it assigns the attention weight to each source word, indicating how relevant that word is for the current output step. Means if the attention is given, soft will become relevant to the teddy bear. You agree? Yes, no?
Yes, yes, yes.
Okay. It's a strong connection or weak connection?
Strong connection.
Okay, thank you. Thank you for interacting. So basically we have uh, attention means what? Creating a rich word representation by encoder, providing a mechanism to understand where to focus. Okay, and decoder will search for dynamic word by word context. So as a whole, if you are using an attention, decoder can dynamically access the most relevant part of the input sentence for each generated word. Okay, means it is very important for natural language processing or language models. Let it be whatever the task may be. Okay, irrespective of the task, they becomes very important. So attention was there since 2014. Okay, the paper on attention came in 2014-15. Okay, but it was not very meaningful at that time until 2017. So why attention is important? It eliminates fixed context bottleneck. It can improve the performance on long sentence, makes the model behavior more interpretable. Okay, laid the foundation for transformer. What is the difference between attention and the transformer attention? Transformer attention is self-attention. Can you understand? It's an attention, but it's in self-attention. So how this self-attention was developed, we'll try to look into the detail. Before we go to the transformer, let us try to understand. Okay, let us start the transformer, then I go to tokenization and embedding program. So transformer architecture was introduced in paper Attention is All You Need in 2017 by Google scientists. Using transformer leads to a dramatic increase in performance over the previously used RNN for generative AI tasks. This learning process occurs through weighted connections between each word and other word within a given sentence. And this mechanism that we call about is self-attention. So during the training, the model learns the weight of these connections and known as attention weights So basically, if you see this architecture of the transformer, it comprises of two blocks, encoder block. Okay, this is encoder. And this is decoder. Okay. So encoder and decoder block. So we'll go through each step in this block. Okay, what is encoder? We start from input, then we try to understand what is input embedding. Then we'll not touch in very detail what is positional encoding. Okay, I'm trying to explain you the math behind it, but without getting into too much confusion. So if you understand, first thing in NLP I have told you is about tokenizer. Suppose I have the sentence, live what you love is the input. Okay, and this is my transformer. So I need to take this input, convert them into a tokens, means numbers. Okay, because neural network does not understand text. They work with numbers. So first step is passing the text to before passing the text to neural network is to tokenize the input sequence.
Okay.
So what is this? Organizer, can you mute this noise background? Okay, so what I was telling is to convert this text into the numbers, we need to do the tokenization. The tokenizer that you choose for doing the training. Okay, the same tokenizer you should use when using this model, means doing inference or generation task. You cannot use the different tokenizers. Okay, so the training time you have selected the tokenizer and the same tokenizer need to be used. So basically what you do first, you convert the text into tokens, means numbers, and these numbers will be converted into embeddings. We call token embeddings. Any doubt here? Any questions? So basically, if you see what I'm talking is this part, the input is taken and converted into the token, and from token we generated the embedding. Okay. So all these embedding or inputs we call x1, x2, x3, x4. Okay. The embedding size will be fixed and all the inputs whatever vectors will have the fixed length. Okay, they will not be variables. Any confusion here? Let us go to some code and try to understand it. Okay, I will not go into the detail of this code, but I'll try to explain you what we are doing is we are trying to use a tokenizer. Okay, to convert the input text into the tokens. Input text into the tokens and then generate the embeddings. Okay, more about this code will be handled in some session called vision language models. Okay, because I'm using here something from that. So can you see, see this text, please? It's visible.
Yes, sir.
Okay, so basically I'm taking a certain model and using some tokenizer. So what is my text? How many text inputs I have? Or what is size of my input text vectors? I have 4 inputs. Okay, 4 sentences. Am I right? So I want to generate the
Yes.
tensors in PyTorch format and I want to use padding. This padding is very important. For example, I have this different length sentence, a brown cat. Okay. Now, what is the length of the third sentence? Say 3 tokens, right? Index 3 is 3 tokens, whereas an airplane is only 2 token. A cookie is 2 token. A donut is a 2 token. Okay. So what will be the output for a donut? The token generated for A in a donut should be same as token generated for cookie sentence a cookie. Okay. The token for A and N should be different. Do you agree? Yes or no? Because all the inputs need to be fixed of fixed size and we have set the padding is equal to true. So there will be a certain symbol or a token generated for beginning of the sentence and end of the sentence. So what will be the how many numbers I'm expecting for sentence a donut? 4 numbers. One is the starting delimiter. Second is the end delimiter. 1 token for A, 1 token for donut. Are you following me? So if I hope my virtual environment is working. Let me execute this. So this transformer is basically I'm using from Hugging Face library. Hugging Face is like GitHub is code repository, right? So Hugging Face is a model repository. Okay. It takes a certain time. So hopefully it will finish first. Okay. So what is the output expected? Output, we have 4 sentences, right? A donut, a cookie, an airplane, a cat. Okay, each has 2 tokens. So for each sentence, we expect 4 numbers to be generated. Are you following me? Anyone? Can you tell me? Okay, let me execute it. So can you tell me what is the code generated for A? And what is code generated for N? A donut is converted into a starting letter 320, 18471, 49407. So what is end delimiter? 49407. What is the start delimiter? 49406. What is a code generated for A? Can you tell me? What is the code generated? Nobody is there to answer me.
Sir, it's 320.
Okay, for N, what is the number generated? The third sentence starts with an N. So what is the number for N?
550.
Correct. So you can see the unique numbers are generated. Now let me change this word, the last sentence with 3. So what will be the output vector size? Currently it is 4 by 4, right? Now I made one sentence with 3 token. So what should be the output vector size or shape? There are 4 sentences, so it will remain 4, but the length of the each token string will be 5. Why? Because for Braun, there will be one word generated. Okay. And all the sentences which are shorter than this will have the padding. Okay. Will have the padding. Can you see there are 4 sentences that I want to tokenize. The length of each tokenized sentence is 5. Why it is 5?
Because brown is the lengthiest word.
Okay, so our entire input tensor should be of similar
One.
dimension, like 5
Yes.
length means all 5. One cannot
All.
be 2, one cannot be 3, one cannot be 5. Okay, that's why this is an important concept, right? Now, if you see what is the token for cat? Cat comes at the before ending delimiter, right? So what is the token for cat?
2368.
Okay, 2368, right? Now, if I remove this padding, means if I remove this brown, 2368 is still there, right?
Yes.
But for brown, the gone, right?
Yes.
Now, what
And
should be the embedding network should able to do? If this is an input, what they should be able to do? They should generate a fixed length vector, right? But that fixed length vector need to be distinct from different words. For example, donut and cookie, both are edible items, right? You agree or don't agree? Donut, you eat.
yes.
Cookie, we eat, right? Both are edible items. So
Yes.
the good embedding should bring these two together very close. But donut and cat distance should be very far. Are you following me or no? Donut is an edible item, cat is an animal. So the distance between donut and cat should be more. The vector that embedding that we generate should be more than the distance between cookie and donut. Why? Because cookie has some similarity to donut in
Yes.
terms of edible item. But cat doesn't have that similarity with either donut or cookie. Okay, so what we do is we now try to use the model. Okay, to extract the text embedding. Okay, so now these tokens will be converted into a vector of 512, irrespective of the input tokens. Okay, the one vector will be generated for each sentence. One embedding is generated for each sentence. Sorry. Are you following me? Now, if you want to see the distance between these two, we can calculate the cosine similarity. Okay, and we try to visualize the distance between them. So if you see the distance between a donut with donut, it's same vector. Okay, the embedding result in same means the distance is 0. The cosine distance, cosine 0 means 1. Cos 0 means 1, right? Am I right or wrong? I think it's not very late, right? So if you consider a distance between a cookie and a donut. Okay, a cookie and donut. Cookie and a donut. What is a distance? Sorry, what is similarity? This is not distance. This is similarity. Okay, similarity is 1 minus distance. Okay, 1 minus distance is a similarity. So the similarity of donut and cookie is very high compared to the similarity between cat and a donut. It may not reflect the very much what you say distinctively here, but when we apply the soft max, the probabilities will change. The probabilities will change. Okay, I don't want to continue this but to show that these are the 4 images I have taken. Then I have taken the embeddings of the image and the text. Okay, so when we take the 2 different type of inputs, then it is called multimodality. Then it is called multimodality. Any confusion? How the token embeddings are generated? So what is the length of token embeddings? 512. What is the length of token embeddings? 512. Okay. In this case. So basically what we have done, we have taken the input, we have tokenized them. From tokenizer, we have generated the text embedding that we call token embeddings. Then from this further, we generate the contextual meaning of these words. Contextual means where they occur. That we call positional embeddings. Okay. So this is what happening in the transformer when you provide the input. What is happening? It is tokenized. After that, token embeddings are generated. Then the words positional embeddings are generated. And then this token embedding and positional and embedding is summed up. And we generate one vector for one word. Okay. One vector for one word. Any confusion here? So if you see this model, we have to prepare this. Sorry. How much time is remaining? I think I'm too slow. Madam, how much time remaining?
Sir, another 15 minutes, sir.
Only 15 minutes. Okay.
No, sir,
Sorry.
if question it is, you can go ahead, sir, after you have the session completed.
Okay. So basically, I want to skip some slides and then. So if you consider this, if you consider this sentence, animal didn't cross the street because it was too tired. Here it refers to animal or street. The word it referring to street or animal.
Animal, sir.
Okay, because how you could understand this, what is coming after it, right, is going to determine the relationship between it and animal. Do you agree? Yes or no? What if it was like this? Animal didn't cross the street because it was congested. Now it refers to animal. Yes, no. It refers to street, right? Now it refers to street. So basically attention should give this meaningful references. So basically if I have the word in sentence, we compute the relational score between word and the rest of the word. If you see that how we compute the values, the it and the animal has the highest relational score, like 0.6. Are you following me? So this is what we will get from the attention. How to do it? We will have certain transformation matrix. Basically, they are learnable parameters, KW, WK, WQ, and WV. We call them transformation matrix for. So basically what we have done right now, we have taken the token embedding, positional embedding. I call it T, I call it P. I add them, and I'll get one vector. That vector I'm going to use for key value and uh, query. Okay. So basically I'm going to generate 3 representation of same word from the single P plus T representation. So one representation is called query, second is called key, third is called value. Okay, all the 3 types will have the same size. Okay, and they are being generated by multiplying the input X with respective transformational matrix to generate the value of Q, K, and V for each word. Okay, after generating an each word, I am going to develop and computing the attention matrix using K into T. Okay, sorry, KT means transformed K, vector transpose vector K, and Q will be dot product. Okay, so I will get one matrix. From this matrix, I can learn how to find an attention. That's why it is called self-attention. That's why it is called self-attention. So now after self-attention, basically this is the diagram for self-attention. So Q and K is taken. We have simple transformation, vector metric transformation. We normalize it, then take the softmax. We'll take the softmax. After taking the softmax, we combine it with V value and calculate the H. Calculate the H. So this is automatically guiding me to the right relevant parts. So this is the all essence of the transformer. So if you have understood this, everything is based on this. Okay, because we got one self-attention. One self-attention is not able to find the language intricacies, means different relationship between the words. So we use multiple of them. Okay, so we call it multi-head self-attention. Same thing repeated H times. So H can be 12, 24, 32, something like that. Not very big like CNN 500 or something like that. So we have same thing repeating for H times for different QKW. QKW. Okay, matrix. So it will give us the different learnable parameters. And after that, if you see that already I computed the multi-head attention. So what is an output of multi-head attention is Z1, Z2, ZH. When I concatenate them, I will get one output of this multi-head attention. One output of this multi-head attention. Now this output of multi-head attention will be added, that is concatenate, and then we take the normalization. So when we take the normalization, we can understand through the attention what is the boundary of the sentence, what is the conference resolution, what is the context of it, what is the comparison, what is part of speech, what is semantic relationship, because of different H. Each H means self-attention, focusing on different item. Okay, so now we will take this input again, and then we take the multi-head attention and combine them. Normalize the multi-head attention and combine with the input. So this part will be done. This part is completed. Okay, then we give this input, which we calculated to feed forward neural network, then perform the non-linearity, which is GALU function. Okay. Then we do the again add norm, this one. So it means that this block will be repeated n times. Okay, this block is repeated n times, and this is called encoder. This is an encoder of the transformer. You understood how we reach the output from here? Now the other part is a decoder, right? So the other part in this diagram, now I'm looking at mask multi-head attention. So we mask certain words, okay, and then we try to produce. So can you see here some dark area and some light area? Light area means the focus need to be done here. Dark means there should not be any focus here. Dark means it is called heat map. No attention need to be given here. The lighter area, the more attention. Okay, so we have the attention mask and the matrix, that multi-head attention that we calculated. So we'll get the mask attention. And based on this mask attention and the values, we calculate the Z dash from this input and norm again. Means basically we are at this layer. Okay, this is equivalent to this. Then we have the another multi-head attention, but it is attention of an encoder plus attention of an decoder. Both need to be combined here. Both need to be combined here. So we do the simple transmission of the two inputs. Okay, one from encoder, one from decoder. Okay, and get the Z double dash as an output. Okay, now after getting this, again we do the feed forward, add norm and feed forward. So I do the add norm. So basically this, then feed forward is this, then again add norm. So it will give me the decoder. Okay, so this decoder will be repeated n times. This decoder will be repeated n times. Okay, so we have the linear layer again, and then we have the softmax layer, which will give the output probabilities. So this is a encoder decoder model used in transformer, but only if representation part means encoder is used. Okay, and only generation part means decoder is used. So there are the LLMs which use only encoder and which use only decoder. The only one which use the encoder is BERT, which is released in October 2018, whereas GPT is released in June 2018, uses only decoder part. So BERT uses pre-training and fine-tuning. There is again self-attention mechanism. This is a summary of whole thing that we did already. So here there is a mask input. BERT is taking the encoder, okay, representation and repeating it n times. It can solve next sentence prediction, whereas GPT is using the decoder, okay, is using the decoder, and it is capable of giving summarization Q&A. So effectiveness of supervised learning is achieved by GPT models. So GPT-3 was released in 2020. I think 2022. GPT-2 was controversial. It was not released. Basically, the main concept here is few shot revolution, and unsupervised learning means I can learn from unlabeled text or generate the text to learn. Okay, GPT-4 is a multimodal capability. Pre-training is a part of any LLM process, and then there is a fine tuning, then there is a prompt engineering. So to evaluate the LLM, we have the different methods. Okay, I cannot run all the code right now, but I want to show the code for audience. So LLM evaluation method, basically, if you see, these are references and these are the predictions. So we will calculate the Blue score and ROG score. ROG scores are of three types: ROG1, ROG2, and ROGL. You can basically see the probabilities that are being generated. The higher the probabilities generated, the better the model is. Okay, that's how we do the evaluation. Okay. So limitations are hallucination, biases, context window, compute cost, and interpretations. Real world applications are many, especially most of the automations will take AI agents or agentic AI forward. Already agentic AI platforms are being integrated into cyber security, network security, network monitoring, etc. I'm open for the questions. Sorry for rushing through the slides, not managing the time well. Floor is open to you all. Yes, any questions? Madam, anyone is there?
Any questions from participants?
So like you talked about evaluation of LLM, right? So
Yeah.
from the perspective of accuracy. So if I want to measure the not accuracy, but the trustworthiness of LLM, how safe it is to use that LLM. So how do we do that?
Okay, okay. To clarify, first thing, the metrics I have told you to find out the similarity of the reference text and generated text. Okay, this is not for safety of the LLM. For safety of the LLM or the specific task, there are separate benchmarks and evaluation methods. Okay. So in safety also,
Okay.
there are different type of biases like conformance bias, gender bias, racial bias. Okay. If you want to see, there is a very detailed study by IIT Madras on biases, especially related to language and races and the regions. Very detailed. Maybe you can find a 70-page report from IIT Madras on biases. You can look, they have created their own references. Okay, based on the uh, kind of fairness they are expecting. Okay.
Okay.
I hope the answer is served. Any other question? Meantime, if you want to connect to me, you can follow this QR link to download my V card, or you can just type this URL. You will get my V card for connection. Okay. Any other questions? You can connect to me over the email, LinkedIn, WhatsApp. Any other questions?
Any questions from the participants? I think we can wind up it, sir.
Okay, madam. Thank you. So
Thank you so much, sir.
just for the viewers, I have some code for reference, like BERT inference, like sentiment analysis, how to fine tune BERT for a specific database. Okay, and LLM evaluation, I think, and image captioning. If organizer provide a suitable means, I can share all the relevant resources, PDF, and the code for and further readings. So basically, I want to give my credits to Shikhar Agnihotri and Langzeli, then the Sanford course, OpenCV, and all relevant papers, and IIT Madras. Thank you, one and all.
Thank you so much, sir. The session was a very good session and it was so much informative. I hope all the participants make a best use of it. Thank you so much for being with us, sir, this time. You are much obliged. And I also thank all the participants for being patient and listening to all the sessions for this day. And there is an announcement for all the participants after this meet. Please take up the quiz and also the kindly fill the feedback form that will be shared in the WhatsApp group immediately after this session. I think we can wind up with this. We'll meet you all tomorrow. Thank you so much. Thank you, sir.
Okay, thank you, ma'am.
Thank you, sir.